So in the flame test lab, we're going to do a couple different things. We're going to look at the emission spectrum of different elements, and then we're going to look at the color of light that certain elements release after being exposed to a flame. This first part, this would be the emission spectrum part. And for turning in this handout, I'm not really concerned with this part, but I'll show you what it looks like. So right here, we have the the different elements, and we took a gas discharge tube and separated the light that is produced from that gas when you run electricity through it. We separate it with a prism into different frequencies, and you can identify different elements based on those frequencies. So once you separate the light produced by hydrogen gas when it's excited with electricity, you get this. You get a red, a light blue, dark blue, and then a couple purple frequencies. Nitrogen obviously looks different than neon and helium, so they all have an individual, unique spectrum. And so what we did in the lab was we looked through a spectroscope and we saw the different spectrums and we tried to match it to one of these four elements. But again, that's not important for the handout. That was just kind of for fun. The other part is a little bit more important. That is the actual flame test part. So basically what we did, we had 6 different elements. We would expose those elements to an open flame, and then it would produce a specific color of light. And we saw that this was orange, and then the next one was pink, yellow, green, red, and then reddish orange. And then you take your sample data that came straight from the lab document and use that to determine the wavelength of each sample. And uh, when you compare your sample data to the colors, you use these numbers over here to fill out the worksheet. So you've got 5.9 times 10 to the negative 7 for orange, then 3.8 times 10 to the negative 7. And notice these are all meters. It could also be nanometers, but I did the conversion for you. We're going to make this simple. 5.7 times 10 to the negative 7 for yellow, and then you can see the rest. So now we have to calculate our frequency and energy. And we'll start off with element D. I'm going to do element D for you, and then I want you to follow maybe not the same exact process, but at least a similar process to do E through I. So for D, first we're going to calculate the frequency. So the frequency of D. Now if you look back at the lab document, you can find everything you need over here in the background. So right here, notice that we have this equation. The speed of light is equal to wavelength times frequency. The speed of light is always 3 times 10 to the 8 meters per second. So we're going to use that information to solve this problem. Now, since we're going to use that equation, we know two things that are given. One is the wavelength, and that's 5.9 times 10 to the negative 7 meters. The other thing is the speed of light, which is 3 times 10 to the 8 meters per second. What's the unknown? Frequency. That's what we're looking for. The equation for frequency is C is equal to wavelength times frequency, but we're going to isolate the frequency variable, and we're going to do that by dividing by wavelength. So frequency is equal to the speed of light divided by wavelength. Now we need to substitute our numbers. So frequency is equal to the speed of light divided by wavelength, and we need to plug in our numbers. The number that we plug in for the speed of light is 3 times 10 to the 8. And notice that the unit is meters per second. That's a fraction, meters per second. Our wavelength is 5.9 times 10 to the negative 7 meters. So if you look at our unit here, we have meters over meters, so we can cancel that. So now the unit that we have left is not a second, it's the second in the denominator, which means it's an inverse second. So we have to punch that in the calculator. So 3 second double E 8 divided by 5.9 second double E negative 7. That gives you 5.08 blah 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 times 10 to the 14th. We're going to round to 2 sig figs, so that's going to be 5.1. So our frequency is 5.1 times 10 to the 14th inverse seconds, or we would also call that hertz, because if you look back at your lab document, a hertz is the unit for frequency, 1 cycle per second. So that's where the 1 comes from, 1 over a second. Now the next part of this is we're going to calculate the energy. So the energy is equal to Planck's constant times frequency. Now for the rest of the lab, when we calculate the energy, and actually for the other examples that you do, after this part right here, you don't have to use the guess method. This is a very valuable method, but to complete the rest of the work, really all you need is to just show what you're doing. So we know that energy is equal to Planck's constant times frequency. So Planck's constant is 6.63 times 10 to the negative 34, and the unit is a joule second. So a joule times a second. And you'd multiply that by your frequency, which was 5.1 times 10 to the 14. Instead of writing a hertz, let's go 1 over a second. It's the same thing, but this will help you cancel your units better. And if you notice right here, see how we have seconds on top, seconds on bottom, cancel. And that leaves us with the only unit left over is joules. So our answer is going to have to be joules. So we punch this in. So 6.3 times 10 to the negative 34th times 5.1 times 10 to the 14th. That's going to give you 3.4 times 10 to the negative 19. The unit, joules. There we go.